So second, 1 second, I need to figure something out. All right, so second right-hand rule, which is for finding the direction of force F. That is, if you have a charge Q present in a magnetic field, so let's say you have magnetic field that points like this, and then in this magnetic field you have a charge Q, and charge Q is moving at speed v to the right, so this is charge Q, and then it moves at some velocity v to the right. And there's going to be a force on it, acting on it, and you can easily determine this by using the right hand. So you'd have the fingers of your right hand point like this in the direction of the magnetic field. This is 4 fingers. And then your thumb points in the direction of velocity. This is the right hand. And so the force itself always comes out of the palm of your hand. This would be the force, and therefore the force acting on this thing would be coming out of your hand. Now, similarly, you could have I wanted blue. You could have a magnetic field that points up, and then you place in this magnetic field not a single charge, but a whole bunch of charges. So you take a wire and you push current through it. This is a conventional current. I'm going to put in parentheses. Conventional current. Meaning it's the flow of positive charges. Flow of plus Q. So on every single Q, you're going to have a plus here, plus here, plus here, plus here, plus here. You have a bunch of positive charges along this wire, and they all flow to the right. That would imply that there's going to be a force on every single one of them that points out of the page. And so you would have a force on the whole current, just pointing out of the page. I'm just going to put a dot here. Yeah, why not? I'll put dots all over the place. So there's a force acting on this whole wire that points out of the page. In other words, the right-hand rule works for both the movement of a single charge Q, in which case this is a velocity, but it can also work for the current. So this in fact implies this. First, second, third, fourth. Here's the thumb, and now what we have is the magnetic field points here, just like before. This is the right hand, and now the thumb points in the direction of the flow of the charges, conventional current I, and then we have the force that points out of the page, force F. So it should be pretty easy to do the following. Let's say that the magnetic field points like this, and then let's say that the current flows like this. This is current I, and then let's say we do another current that flows to the left instead. Here's the second current, so let's label this as I1, let's label this as I2. Now let's maybe do a few more examples. So suppose that we have a magnetic field that points into the page. Magnetic field points into the page, and then we put a wire carrying a current. And let's say that this current flows like this. So here's I1. And then let's say we have another current that some odd reason starts here, flows to the right. We could make this work if we just ran this out here and then connected it to the battery, then brought this thing back. So in this little section, the current flows to the right. This section it flows down, and this section it flows up, and then here it flows back. Right, positive, negative terminals of the battery. All right, so now let's determine the forces acting on these wires. So here, this one. You can pause the video, try to figure out the direction of the force by yourself, and then replay this, restart the video, and see what I'm doing with it. So for this one here, I would draw the right hand like this, where I have fingers pointing down along the lines of the magnetic field, and then current I points to the right. Just remember, this is the right hand, so the only way this could work is if the force on this wire pointed into the page. I would have force F pointing into the page on this wire. On this wire here, I would have to draw the fingers point down. Now let me stick with the black. So here the fingers point down in the direction of the magnetic field, and then the current points to the right. So this is the direction of the thumb. Now this is the right hand. So the only way this could work is if I had the force acting on this wire were pointing out of the page. Wait a second. Oh, I see. Well, we'll have to fix an error. But anyway, so this is pointing yeah, this is pointing out of the page. I'm going to put here out of the page. And then let's go back to this one. This one here would be actually into the page. The other one here is into the page. So this is X. Confirm that's true. Yeah. The other one. Yeah. All right. So now let's do these here. Let's do this wire. So this would be tricky to draw. So I'm just going to go ahead and I'll just figure out the direction. I'm going to have the fingers, my fingers pointing into the page, into the screen, and then the current flows down the screen. So, and I'm using my right hand, so the force must point to the right. So I would have the force here pointing to the right on this wire. Maybe I'll put one more here. So on the whole length here of this wire, there's a force that points to the right. Now this little segment here of this circuit is in the magnetic field, and the current here points into the page. The magnetic field points into the page or into the screen, and then the current flows to the right, so the force points up out of the palm of my hand. So force on this one would point up. Let's do this little section here. The force would point to the right. This little section, there would be no force because this section is outside of the magnetic field, so this would be 0. And this section of the circuit here, the force on this one would also be 0 because this section of the wire is outside of the magnetic field. All right, and that's about it for the right hand rule.